In the next subsection, we'll talk about binary search trees. For now, that might seem disconnected to what we just talked about, but you will see what's coming. Okay, again, I would expect that for 2/3 of you, this is known. And this is my proxy question to find out if that is true. So without telling you what a binary search tree is in this class, let's have a go at this. Yeah, again, there's another name for the same thing. Fundamental things have often been called different ways. No, okay, I should have checked how many signed in for the 59. That's got at least 55, right? Okay, 56. Yeah, good. No, that's not what I wanted. Well, I kind of gave the answer away, which is not a problem. I keep doing this, right? It's, the thing is, okay, people are changing their minds now. Remember, it's just about participation. I think the true picture was half or slightly more of you remembered, like before, so it's not really a surprise. I do want to give the answer away here. Okay, do I? Well, we'll discuss this in detail. There are some shortcomings of binary search. I didn't discuss this in detail on the slides, but one shortcoming, which is maybe a bit academic, esoterical, it needs arrays. And maybe we don't like arrays because we don't like arrays. The real shortcoming of binary search, or a dictionary implemented as a sorted array with binary search for get, is how do you update it? How do you insert an element that has to go somewhere in the middle? It's an array. You have to shift all the elements over, so you're spending worst case linear time again for the update. You can quickly find where the element has to go, but there's painstakingly effort. You have to move all the elements before you can get a new element in there. So it's virtually useless. So what binary search trees are, you should think of the key concept is it's a dynamic sorted array. It can behave like an array. It's not quite as fast for access than just jumping to the 15th position in an array. But it's virtually doing everything that an array can, plus allowing you to insert at any possible position. Okay? I think that's a way it's not often phrased, but that's the cool way. I think this is, if I told someone who doesn't know this, make that happen, make an array where you can insert at any point and it's still fast, they're probably stuck for a while. Okay, we've already talked about binary trees. So you remember this is a construct where we have nodes and they have pointers to left and right children, and they have a value associated with them. In this case, I really should say a key. They have a key associated to them. If you wanted to have some UML style diagram as I had them before for a node, we should have 4 fields really. A pointer for the left child, a pointer for the right child, a key, and then a value. Okay, I told you what it should read. It's hard to read. Again, the value pointer is not very interesting. There's nothing really happening with that one, so we'll mostly ignore it. But we'll have a key associated to each node. that part's the same. Binary trees is the same as for heaps. That's also why people often confuse it a bit. So don't do that. They're both binary trees. The rest is different though. Plus, second property, also no complete binary trees, right? This is unrestricted. It's okay for a binary search tree to have all sorts of gaps. It can look like this. Okay, that's a valid shape. For heaps, we didn't like that. Second big property, that's the important one. Everyone listen up. The search tree property, or symmetric order trees. If you have any node, that's the root of some subtree. The key in that root element has to be bigger than everything in its left subtree, all the keys in the left subtree, and it has to be smaller than everything in the right subtree. Now, if any of the two subtrees are empty, that statement also makes no restriction. If there are elements, they have to satisfy this. Okay. Here's an example. That's some binary search tree shown in the way that I think binary search trees must be drawn if you want to understand how they work, which means you lay them out so that the root vertically separates the two subtrees, and you do that recursively. So the root key is projected down like this. Then the root of the left subtree is projected down here and separates its two subtrees and so on. Can you see how this picture is generated? And then you see how the search key property naturally gives you back the sorted list at the bottom. And that's really just by definition. The key of the root here, projected down here, everything in the left subtree is supposed to go to the left of it in the picture. And the search tree property exactly says all these keys should be smaller than the key in the root. And so if you do that for every node, you end up with the sorted list. All right. Should maybe comment the little square boxes. These are null pointers. I included them in these pictures because they make insertion a bit clearer if you explicitly draw them. But in Python, or if you implement this, every of these nodes really is one of these boxes is an object with a few fields, a left pointer, right pointer, which can be null, and a key, and so on. All right. I'm supposed to show you some interesting example of how we find an element. Let's use the same example as before. Let's use the 69. How can we find in this tree without looking at all the nodes, right? How can we find where the 69 is contained? Well, one thing I haven't said, we always keep a pointer to the root of the whole tree. That's what we need to get started. So we start at the root, and now we do something similar to binary search. We compare 69 to 77, it's smaller, so we have to go left. So we follow the left pointer to this one. Now we find that 12 is smaller, so 69 is bigger. And then we follow the right child, because the logic behind this is, at this point, I know when 69 is already bigger than 12, there's no point in looking in the left subtree because all of these keys are even smaller than 12, and 12 already was too small. Same as binary search, just that we don't really have to jump into the middle of anything. We're following the topology of the tree, and that tells us what to do. And here we find it. And so I'll say this one more time. At this point, we won't just stop. We will return the value that is also stored in this node, okay? But from now on, I'll ignore that last bit. We'll always just carry these value pointers around with us. There's never, ever anything interesting happening. Let's do one more example where we search for something that's not there. I don't know. How about 88? So if you try to find 88, we start at the root again. 88 is bigger than 77, so we take the right pointer. It's also bigger than 85, but smaller than this. And at this point, we end up in a leaf, or a null pointer. And that's the signal, it's not there. If it was there, it had to be at this position, but there's nothing, so no element there. And again, I invite you to mentally project down this left and right zigzagging onto the horizontal, onto this axis. Then you see it's doing similar things like binary search. Good, so we can still do binary search. Question?
You told that when we found it 69, we returned the value. So
yep.
Value means the pointer or the next node 63 you are saying?
Oh, so what I meant is every node, so every circle in the picture, stores a key and a value. Yeah. And okay, I said pointer because I thought this helps you with Python. Like if you're just learning Python, maybe this was not very helpful. Everything in Python is an object, so every value that is something is really a pointer to an object. That's what I meant. You can think of it, every node stores a key and a value. And when you found a node that has a key that matches the one you're trying to find, you return the value that this node stores. That's all. There's nothing complicated going on. Okay.
These numbers are the node numbers. We are searching through the node numbers, not the actual values.
What's the difference between the node number and the actual values?
No,
or
you say that this is the key and the values are storing differently.
Yeah, so maybe let's zoom into one of these just to make that clear. Say we have 77, right? And let's say we zoom into this. If you look very close, then what it really looks like is this box, and it has the 2 pointers, and it stores 77 and some value that we associated with it. Who knows? Maybe the string 77. I'm just making this up, right? The dictionary can store whatever is convenient. And it would have 2 pointers. Now, let's say this one would point to this object, and this one would point to that object. Now I'm completely messing up the slide, but yeah, last year I didn't talk about the values at all, and then people got confused. Now I talked about it, and I think I confused you even more. I'm iterating this. I hope it's clearer now. Good. So finding things in a binary search tree is just like binary search, and we could already do that on an array. So that's not really where things get interesting. So let's do something interesting. I praised these as being dynamic, so let's insert something. Most operations actually start by trying to find the element. And that's natural. If you want to insert something in a dictionary, remember this is really the key, and there's a value associated with it, and we require that every key is only there once or not at all. So we start trying to find 88. It's bigger than 77, so we go right. It's bigger than that, and it was smaller than this. So the search ends in this null pointer. Now that signals 88 is not yet in the tree, which is good. We want to insert it. So what we do now is we create, well, this is just drawing the picture differently, okay, back and forth a few times. It's just making way on the picture. The data structure hasn't changed. But then we can create a new node and add it as the new left child of this node 97, where the search stopped. Okay? So the search brings us to some node that has a null pointer, and we should replace this null pointer by the new element. That's where the search left us off. And so all that insert has to do is create a new node and stick it there. Okay? Pretty easy, right? Okay. Dynamic means not just insert, also delete should work. Let's have a quick look at that as well. And here things are a tiny tad more complicated, but not too crazy. But there's these three cases. And let's do one example each to illustrate this. If we want to remove 11, well, first of all, okay, it's there, so we'll find it. To find out whether it's there, we do a search. Same process as before. So we found 11. Now we'd like to get rid of it. And in this case, we can just go ahead. It's easy because 11 is a leaf in the tree. It has no children, just null pointers. So we can just remove it, which means in 12, set this one to a new null pointer. And that's all that's needed. Okay, and then we have removed this element. Things are only slightly different if the element that we find is one with a single child. So 69 has one child, but the other one's null. In that case, we can still just remove the node, and we can shortcut. We can jump over this node that we delete and just put the single child that 69 had as the new child of its parent. That's, again, not such a big deal. And the troublesome case is, as you may guess, when you want to delete something that has two children. Because then you can't possibly stick both children in the parent pointer. There's only room for one. So there's different ways how you can solve this. The easiest that we will do is you continue a search and you find the element that's just smaller than 85. So the largest element that's in the dictionary, but smaller than 85, which always means you go first one to the left and then to the right as long as you can. That always gets you to the predecessor in the search tree. And then you swap these two, which could just mean replacing key and value. Okay. And now, why does this work? Why does this not destroy the invariant of the search tree? The reason is that these two were adjacent in the array. Why is this 72? Anyways. So these two are adjacent in the array. There's nothing between them. So after we've removed this one, that one is still in the middle of the right subtree and the left subtree of this node. So it can just take this one's place. Okay? So we've removed this one, but we might have to recursively remove this node. But because it's the predecessor, we follow right links as long as we can, so it always has at most one child. So the second bit, this doesn't cascade. The second will always be a simple case, either easy or medium. Okay? I guess you're now bimodal. The half is lost and the other half is bored because they've seen this. So the average is happy, right? I promise there will be other kinds of topics in the future. No valuation. Let's briefly analyze how expensive all these operations are. Now, a search, if you remember, we always had some tree. It may look in all sorts of ways. And the search followed some path down the tree. Okay? That depended on the key. But in either case, the length of this path is at most the height of the tree. Remember, the height is just the maximal number of edges on any root to leaf path. So it's kind of by definition the longest path we can follow if we just go down. If you want to count the number of comparisons, so if the height is h, then the number of comparisons we make is at most h plus 1 because you need to compare at the node where you start and at the node where you stop. You might get away with one less, because if you end up with a null pointer, maybe you can be done early. And also, you can be lucky if you're looking for an element, you find it in the root, then it's just one, but it can't go on for more than the height of the tree. And one more for the final node. If you remember what insert did, insert walked down a path and found a null pointer and then stuck the element there. So it's dominated by the search. And again, we have the basically same number of comparisons. We just have to create a new object at the end and stick it there. No big difference. And delete is a little more tricky if you look at the different cases. But even the hard one, if you combine the two orange paths that we followed, so if you have a hard case, the first search stops somewhere in the middle of the tree. But then you continue from there. So in total, you still just follow one big path. And so again, it's bounded by the height. So it's really, everything depends on the height of this binary search tree. So I summarized this here in terms of the abstract data type operations. If you want to construct a tree, unlike for heaps, there's no really smarter way than inserting one after the other. So we might as well just do that. That's n insertions, and each is bounded by the final height. Right? If you just do insertions, the tree will only ever grow. So the final height is a bound for all the heights in between. All the other operations are essentially doing one search plus a little bit of extra things. But if we ignore the exact count of operations, if we allow ourselves this fudge using big O notation, ignore constant factors, they're either bounded by the height or they're even faster. So the height seems to be pretty important. What is the height? What can it be in the worst case? And the unfortunate answer is it can be pretty awful. And the example is quite clear. If you insert elements in sorted order, the binary search tree you get will look like this, because you always, if the new element you insert is always bigger than any before, you always follow the right paths until you find the rightmost leaf and stick the new element there. So it's not just an unfortunate case, it's also something you can run into fairly naturally if you insert things in sorted order. So you really shouldn't do that. The good news is also a rare and pathological case in some other sense, namely in the average case. If you can somehow make sure that the insertions are not sorted, and it's really enough. So if they come in random order, that's fine. Then you get logarithmic height, which, remember from heaps, that's the best possible. The only question is what the constant inside this here is. So the constant might not be optimal, but it's close to optimal if things come in random order. And you can even prove slightly more sophisticated statements. Under this model, it's not just the expected height is good, but also it's very rare to see a bad height. You can prove things that it doesn't have to be quite completely random. But there's some caveats. If you also add deletions, things become a bit more tricky again. So for us, we'll mostly just say the height is normally good if you don't have really unlucky inputs. Question? Yeah, so we'll come to that. The question was, can you rebalance the tree? And so that's exactly the answer to that. We'll revisit that at the end.